Hello everyone, we're solving this chemistry paper today. This is February-March 2021, 9701 paper 4.2. Okay, this is paper 4, variant 2. Let's begin, shall we? Before we start, I just want to talk about the threshold. So, this was by far one of the hardest papers I've ever seen. This is Feb-March 2021. I'm gonna drop a link for the threshold down below. Out of 100 marks, A was at 53, B was at 42, C was at 37, D was at 32, and E was at 25. Okay. So A star would have been at around, maybe 70 to 75, that range, because it was such a difficult paper, right? It's difficult when A is at 53. 50 is like half the total, right? Anyway, I actually made a form for question paper requests. I'm gonna add that in the description and comments below. So fill that up if you want me to solve more papers. I'll know what you need. But for now, my plan is to complete chemistry paper for 2021, at least for now, right? About the May June 2022 papers, I'll do them when they come out on August 11th. So if you like the video, remember to subscribe to the channel if you haven't already. It will help me a lot. Let's begin. Question 1. The most common oxidation states of cobalt are +2 and +3. Complete the electronic configurations of the following free ions. So this is the shorthand electronic configuration, right? Since we have argon given already. So there's been a change to the question paper from 2022. Previously we had the data booklet. So when I solve papers pre 2022, I'm always going to be using the data booklet, okay? But from 2022 onwards, I won't have access to the data booklet. I won't use it anymore. Okay, you can check out my March 2022 or specimen paper 2022. I did not use the data booklet there. So any data you need will be provided in the question paper itself. Understood? So let's see. Let's look at the periodic table. Cobalt, right? Cobalt is located over here. So it's 1s to 2s2, 2p6, 3s to 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 3, 7. Okay? So it's cobalt is in general 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. That's cobalt. Now the electronic configuration for argon is 1s2, 2s2, 2p6, 3s2, 3p6. That's argon, right? So it can be written as argon followed by 4s2, 3d7. This is the electronic configuration for cobalt. Now if you want to write cobalt 2 plus, always remember for transition metals, the electrons are taken out of the 4s orbital first. So it's going to be argon followed by 3d7 only. Okay, it's 4s0. You can write that if you want. It's not really necessary. What about cobalt 3 plus? We're going to remove 2 electrons from the 4s orbital and 1 electron from the 3d orbital. So what do we have left? It's argon followed by 3d6, 4s0. 4s0 is not a requirement, okay? Moving on. Cobalt 2 plus and 3 plus both form complexes with ethylene diamine tetrastric acid. It's EDTA, bidentate ligand. Use the data in the table to predict what happens, if anything, when separate aqueous solutions of cobalt 3 plus and cobalt EDTA, a complex of cobalt and EDTA, are left to stand in the air. Okay, so an aqueous solution of cobalt 3 plus. Okay, So basically, we're gonna see whether oxidation occurs. Like, you know what happens with iron, right? Iron 2 plus, it's a green precipitate. It turns brown when it comes in contact with oxygen, the air, basically, right? So something like that. Let's see. So yeah, iron is oxidized, right? So let's check this out. So here we have cobalt 3 plus, right? We're looking at this equation, and we're going to deal with oxygen over here. So look at this equation. Cobalt has a reduction potential of 1.82. Oxygen has a reduction potential of 1.23, right? What does that mean? Cobalt will be reduced to form cobalt 2 plus, whereas since it's a aqueous solution, it has water in it, right? Water will actually be oxidized to form oxygen gas. To balance this equation, what do we need to do? Balance the number of electrons, multiply this thing by 4, 4, 4. So we can get rid of these. It's going to be 4 cobalt 3 plus 2 H2O is equal to 4 cobalt 2 plus 4 H plus and oxygen. That's it. So what can we actually say? This was only possible because the reduction potential of cobalt 3 plus was greater than the reduction potential of oxygen. Okay, so cobalt will be reduced instead. So cobalt 3 plus is reduced to form CO2 plus. So oxygen gas or O2 is evolved. Why is this? Because the E value of E or reduction potential of cobalt 3 plus is greater than the reduction potential of oxygen. So these are three separate points, by the way. Okay, 1, 2, 3. What about an aqueous solution of copper with EDTA? uh, this one has a reduction potential of 0.38, right? So if you compare 0.38, right, with this reduction potential, oxygen has a greater reduction potential. Okay, so if you want to oxidize water, right, we need to take the oxidation potential for the second equation. That would be minus 1.23, and this actually gives us a negative value, right? Minus 1.23 plus 0.38, that gives us a value of minus 0.85. Okay, so this reaction is not possible. This cannot be oxidized to form this. When it reacts with water, a redox reaction will not occur. On the other hand, you could say that copper EDTA2 minus could be reduced to form copper EDTA minus. Okay, 2 minus forms minus. So the reaction down below, this is actually not feasible. So it's not good. It's going to be no change, right? No change to cobalt EDTA minus, or we could say that it's not feasible. Okay, because the E of cobalt EDTA minus is less than the E of O2. Okay, that's basically it. By the way, they might be asking another question. What if you had cobalt 2 plus? Would it be oxidized to cobalt 3 plus, like iron 2 plus to 3 plus? Look at this. Cobalt 2 plus to cobalt 3 plus is actually minus 1.82. And the reduction potential, this is the oxidation potential of cobalt, and the reduction potential of oxygen is plus 1.23. If you add this up, you're going to get a negative value. So that's also a no-go. Cobalt 2 plus wouldn't be oxidized, okay? So there are two possibilities here. Either you could say that cobalt 3 plus will be reduced to cobalt 2 plus, or you could say that um, cobalt EDTA 2 minus would be oxidized to cobalt EDTA minus only. That's a possibility, okay? But cobalt 2 plus won't be oxidized to cobalt 3 plus, and cobalt EDTA minus, right? This is basically cobalt 3 plus here. This cannot be reduced to cobalt 2 plus EDTA, okay? Net charge being 2 minus, that's not a possibility. Remember this. To be feasible, the net value of E cell must be positive. Anyway, number C, hydrated cobalt to nitrate is a red solid that behaves like hydrated magnesium nitrate when heated. Describe in detail what you would expect to observe when crystals of cobalt nitrate, 6 waters of crystallization, are heated in a boiling tube gently at first and then more strongly. You guys know that in general, a group 2 nitrate, right? It forms magnesium, the metal oxide, 4Na2, the brown gas, and oxygen gas, okay? But there's another observation. Since these are hydrated crystals, they will also form steam. So you can say that at first we will see condensation on tube, or you could say that steam is evolved. That's the first point. Next, brown fumes or brown gas is evolved. Okay, what else? A colorless gas will be formed that relights a glowing splint. Anything else? It's heated gently at first and then more strongly. So the magnesium oxide, or the cobalt oxide, basically dissolves and turns into a liquid. This is only possible for the oxides at the top of the table. Okay, it wouldn't be possible for barium oxide, for example. It has too high a melting point. Okay, but since they told us that cobalt behaves like magnesium oxide, magnesium nitrate basically, so it would give us the same observation. So the solid, that means cobalt nitrate, which turned to cobalt oxide, would then dissolve. Solid dissolves. Okay, or we could say that it turns to liquid. Now, explain why the thermal stability of the group 2 nitrates increases down the group. Really important question, guys. Mainly the reason being, as we go down the group from magnesium, calcium, strontium to barium, what happens? We have the same charge, but the size increases, right? So the cationic radius or ion size increases down the group. Understood? That's point number 1. What about point 2? As the size increases, there will be less polarization of the anion, right? Because according to Fajan's rule, as you increase the size of the cation, the polarization, the polarizability of the cation actually decreases, right? So the polarization of the anion cloud will also decrease. Less polarization or distortion of nitrate ion anion NO3 minus occurs. Okay, really important question. Moving on to question number 2. Iron 2 compounds are generally only stable in neutral, non-oxidizing conditions. Okay, it is difficult to determine the lattice energy of FeO experimentally. So, use data from the data booklet and this Born-Haber cycle to calculate the lattice enthalpy of FeO. Okay, so the Born-Haber cycle is given. Let's look at the steps, right? So to form FeO, we need 1 mole of iron and 1 mole of oxygen atoms. Okay, that's why we're using Fe solid and half O2 gas, because oxygen exists as a diatomic molecule, right? So 1 molecule or 1 mole of oxygen gas molecules contains 2 moles of oxygen atoms. That's why we're using a half in front of it. Okay, so this minus 272, as you can see, this is the enthalpy of formation, the direct route from the elements. The enthalpy change from when 1 mole of a compound is from its elements in their standard states under standard conditions. That's the enthalpy of formation. What's the other route? Basically, look at this plus 416. This is the enthalpy of atomization of iron. Iron was converted from solid to gas. Then, as we go from this step to this step, right? As we go from here to here, we are getting one molecule, 1 mole of oxygen gas from half oxygen, half moles of oxygen molecules. So the enthalpy change when 1 mole of gaseous atoms is formed from its element, right, in its standard state under standard conditions, is called the enthalpy of atomization. So the data for this is not given. We need to use the data booklet. As you guys know, um, enthalpy of atomization, remember, enthalpy of atomization is half the bond energy. Always remember that. For oxygen, the bond enthalpy is 496. Okay, the bond enthalpy is 496. So the enthalpy of atomization of oxygen should be 496 by 2. I'm showing you that in a bit. What else do we have, guys? As you can see, from this step onwards, we convert iron to iron 1 plus and then iron 1 plus to iron 2 plus. Okay, so these are basically the ionization energies for iron and iron plus. That's logically it. The enthalpy of atomization of oxygen followed by the ionization energy, first ionization energy of iron and the second ionization energy of iron. Okay, so check this out. Let's look at the bond energy for oxygen. So the bond energy for oxygen is 496. So the bond energy of the oxygen double bond, is 496. So as I was saying, the enthalpy of atomization, right, it is half the bond energy, so it should be 496 divided by 2. So that's one of the things we need. What else? Basically, we need the ionization energy of iron. The first ionization energy, since we need Fe2 plus, we need the first and second ionization energy. The first IE is 762 and the second IE is 1560. Those are the basics, right? So let's see. So as I was saying, the enthalpy of atomization of oxygen is 496 by 2. The first ionization energy of iron is 762. The second ionization energy of iron is 1560. Okay, and the electron affinities will always be given. All right, they can't be found in the data booklet if you're doing sums pre 2022. They will always be given. The first electron affinity, right, is always exothermic, while the second electron affinity onwards is always endothermic, and that's plus 798. Okay, and we need to find this out, lattice enthalpy. So this is essentially a Hess cycle. This is one of the routes and this is the other long route, but they will be equal to each other. Okay, so let's see. If we start doing this, it's plus 416 plus 496 by 2 plus 762. I'm just following the arrows. Plus 1560 minus 141 plus 798 plus the lattice enthalpy, right, is equal to this enthalpy formation minus 272. So if you guys do solve this, you're gonna get your answer as minus 3915 kilojoules per mole. So that's it, right? Moving on to question number 2. Most naturally occurring samples of iron 2 oxide are found as the mineral wastite. I don't know the exact pronunciation. It's German or something, right? So wastite has formula Fe20OX. It contains both Fe2 plus and Fe3 plus. 90% of the iron is present as Fe2 plus and 10% is present as Fe3 plus. Okay. So how do we solve this? Basically, you need to understand that there are 20 iron atoms in each unit. So out of those 20, 90% is iron 2 plus, 10% is iron 3 plus. According to the rules of oxidation number, the net oxidation number must be equal to 0. Oxygen has an oxidation number of minus 2. And there are X atoms of oxygen present in the compound. We don't know how many, but there are X atoms of oxygen. Okay. So here's the thing. 90% of 20. How much is that? 90 by 100 into 20. That's 18. Okay. So 90% of 20 is 18. There are 18 Fe2 plus molecules and 10% of 20 is 2. There are 2 Fe3 plus molecules. Do you understand? So that's 90 by 100 into 2. So 90 by 100, right? Into 20 into 2. So this is the way they did it in the mark scheme. Okay, I'm going to show you another way, a way which is easier for you guys to understand. Essentially what I did was 18 into 2 plus 2 molecules of iron 3 plus into 3 plus minus 2 into x molecules of oxygen, x atoms of oxygen is equal to 0. If you solve this, 18 into 2 plus 2 into 3 divided by 2 gives you an answer of 21. So there are x moles of, or x atoms of oxygen, basically. All right, so that's the logic. First, I multiplied 90% with 20. Okay, first I multiplied. This is what we did actually. 90 by 100 into 20 into 2 plus 10% of 20 of all the of the total iron atoms basically into 3 plus. Okay, minus 2 into x, because each oxygen atom has oxidation number of minus 2. The total oxidation number of the compound will be 0. All right, that's the logic. So what they did in the mark scheme essentially is that they took 20 common. Do you guys understand? This is the route they took. They actually took 20 common from that side. So what do we end up with? 90 by 100 into 2 plus, right? Plus 10 by 100 into 3 plus. Okay, that's what they did. minus 2x is equal to 0. That's how they solved it, okay? But you could do it in the orange way as well, the one I used down there, all right? Hopefully that makes sense. If you solve it, you're going to get 21 atoms of oxygen. So Stanley explained how the lattice energy of iron oxide compares to lattice enthalpy of calcium oxide. Okay. So Fe2 plus Ca2 plus, both have the same charge and both have the same anion. Lattice enthalpy depends on two things, the charge as well as the size of the ions involved. So the charge is the same. Let's look at the size. If you think about iron and calcium, okay, let's look at the data booklet, then everything will make sense. Let's look at the periodic table. You will have access to the periodic table post 2021. Compare calcium and iron. Remember the trend across the period, you learned this in AS. As you go across the period, size decreases. Okay, so the size of the iron cation is smaller than the size of the calcium cation. I can give you more proof. Check this out. So calcium is 0.099, iron is 2 plus is 0.061. That's much smaller, right? So what can we say? Fe2 plus has smaller radius or higher charge density due to it having the same charge. It also has the same charge, right? It has the same charge as calcium, but a smaller radius. That's why it has higher charge density. All right. Now what? That's your first point. The second point is, so iron oxide has a more exothermic, or you could say it has a more negative lattice enthalpy comparatively. Now we're going to give a reasoning. Why is it more exothermic? This is because there is greater attraction. This is because there is greater attraction or stronger ionic bonds between Fe2 plus and O2 minus, the oxide anion, compared to calcium and the oxide anion. Okay. Moving on to question 2, part B. Heating of iron oxide results in the formation of Fe3O4. This is ferrosoferric oxide, as far as I know. We have ferrous oxide and ferric oxide. So Fe3O4 is a combination of FeO and Fe2O3. Basically, iron 2 oxide and iron 3 oxide. If you combine these two, you're going to get Fe3O4, ferrosoferric oxide, okay? Each formula unit of Fe3O4 contains 1 Fe2 plus and 2 Fe3 plus ions. Okay, show how reaction 1 can be described as a disproportionation reaction. What is a disproportionation reaction? It is a reaction in which the same species is both oxidized and reduced simultaneously. Check this out, guys. Fe has an oxidation number of 2 plus here. It goes from 2 plus to 0 here, it is reduced. It goes from 2 plus to, 3 plus over here. That means it's oxidized, okay? So let's write that down. Fe2 plus is reduced to Fe, or we could say that oxidation number of Fe goes from 2 plus to 0. What about the other one? Fe2 plus is oxidized to Fe3 plus in Fe3O4, or you could say that the oxidation number, right, goes from of Fe goes from +2 to +3. That also works. Any one works, okay? Now what? Fe3O4 can be electrolyzed using inert electrodes to form iron. Okay. So clearly, guys, this is not aqueous, by the way. This is liquid iron oxide. That means it only has three ions actually. The cations are Fe2 plus and Fe3 plus, since it's the molten compound, not aqueous. If a compound is aqueous, it also has water molecules, hydroxide ions basically, and the anions are O2 minus only. That's the only one available. Okay. Now here's the thing. Basically, cations go to the cathode, right? Cations go to the cathode, and that's what happened. We got iron at the cathode. Okay, basically iron 2 plus or 3 plus or both of them actually went to the cathode to get reduced to form iron. On the other hand, oxide oxide anions, they will go to the anode to get oxidized. Okay, there are two types of electrolysis, by the way: electrochemical or the galvanic cell, or electrolytic cell. We're talking about the electrolytic cell. We don't need we basically need a battery here, right? We don't need a galvanometer, we need a battery. This is non-spontaneous. So the anion, the only possible anion is oxide. Okay, so it has to go to the anode to form oxygen gas. That's how I figured out that this will be the half equation. Okay, oxide will form oxygen, and to form one molecule of oxygen we need two oxide ions, and the net result will be a loss of 4 electrons, right? So if you want to see the data booklet, let's see if it's available. Let's look for oxide, right? I don't think we have this in the data booklet. Plus, you won't be given this data booklet anymore, okay? From 2020 onwards, you won't be given this, but you need to answer these questions. So we just used common sense, right? Because oxide is the only available anion, so it will go to the anode, and from oxide we can only end up with oxygen after oxidation, okay? So that's it. How did I figure things out though? This has an oxidation number of -2. This has an oxidation number of 0. Okay, so it went from -2 to 0. For each one, we need to lose 2 electrons, but since there are 2 oxygen atoms, we need to lose 4 electrons in total. Get it? Moving on, calculate the maximum mass of iron metal formed when Fe3O4 is electrolyzed for 6 hours using a current of 50 amperes. Assume that one Fe2 plus and two Fe3 plus ions are discharged at the same rate. So something really funny happened. Uh, Basically, my student gave me this sum to do a few months back. So he wasn't able to do it, and I wasn't able to do it either because we didn't see this line actually. Assume that one Fe2 plus and two Fe3 plus ions are discharged at the same rate. This line has significance, alright? What does this indicate? I'll teach you. Basically, Fe3O4, right? It has both Fe2 plus ions and Fe3 plus ions, okay? But what's the ratio between them? Like for each Fe2 plus, will we get like reduce one Fe3 plus? For each Fe3 2 plus, will we reduce three Fe3 plus? Does it work like that? Basically, uh, this is what the line indicates. Assume that one Fe2 plus and two Fe3 plus ions are discharged at the same rate. Okay, so for one Fe2 plus reduced, we will get two reduced Fe3 plus ions. Okay, that's the logic basically. So let's see. This is the equation. Check this out. For one Fe2 plus, we will also discharge two Fe3 plus, right? To get iron. Now here's the thing. How many iron atoms will we get then in total? Basically, we'll get 3. Okay, one Fe2 plus and two Fe3 plus. And how many electrons need to be transferred in total? For each Fe2 plus, it needs to gain 2 electrons. For each Fe3 plus, it needs to gain 3 electrons. But since there are 2, the total will be 6 electrons. So 6 electrons for Fe3 plus and 2 electrons for Fe2 plus. We're getting a total of 8 electrons will be gained. Understood? For each discharge of 1 Fe2 plus and 2 Fe3 plus, 8 electrons will be gained, and we're going to get 3 atoms of oxygen. So let's see the maximum mass of iron metal that can be formed using a current of 50 amperes. We know that Q is equal to IT. The time is 6 hours. You cannot use hours, you need to convert this to seconds. So 50 into 6 into 3600 gives you 108,000 coulombs. Now you can find out the moles of electrons by dividing it with the Faraday constant 96,500. We're getting an answer of 11.2 moles of electrons. Now here's the thing, let's do the molar ratio. We want to find out the mass of iron. What's the molar ratio of electrons to iron? To find out the moles of iron, what do we need to do? Basically, what's the molar ratio? It's 8:3, right? So it's going to be 11.2 moles of iron divided by 11.2 moles of electrons divided by 8 into 3. That will give you the moles of iron actually, okay? 11.2 moles of electrons divided by 8 into 3 gives you the moles of iron. That's 4.20. Now to find out the mass, you can take the value of AR from the data booklet. That's 55.8 for iron. If you multiply it with 4.20, you're going to get your answer as 234. 4.2 into 55.8 gives us an answer of 234.36. You can opt to write 234.2. Wait, sorry. Yeah, 234 works. 234. 108,000 by 96,500. That's actually 11.19, yeah? Divide by 8 into 3. That's actually 4.1968 into 55.8. If you use your calculator answers, you're going to get this value 234.19. Okay, 234.19. Or basically 234.2. You can either write 234.2 or 234 grams. Either one works, okay? Moving on. Lithium iron phosphate. Lithium ion, these are used in lithium ion rechargeable batteries. Basically the ones used in our phones, right? We charge them every day. When the cell is charging, basically we don't have these. This part is excluded from our syllabus. This part, okay? This isn't any in our syllabus anymore. This was present in our syllabus from 2016 to 2021. From 2022 onwards, you don't have this part, okay? But you should have an idea about lithium ion rechargeable batteries. Basically, they're very small. They're compact. They have a low size, low mass, okay? That's why they're like, this is a very good advantage. There's another advantage. You could say that it can supply a high voltage. Explains why it can run our phones, right? When the cell is charging, lithium reacts with the graphite electrode to form LiC6. When the cell is discharging, the half equations for the two processes that occur are as follows. Use the cathode half equation to determine the change, if any, in oxidation states of lithium and iron at the cathode during discharging. Let's try to figure this out, right? Come on. At the cathode. So we're looking at this essentially. Lithium and iron. So lithium is +1 over here. Phosphate is -3, right? So iron needs to be +3. Now over here, phosphate is -3. Now lithium has only one possible state, okay? It's +1. Group 1 metals can only be +1. So if it's in a compound, it has to be +1. But iron, look at this. If I want to balance this, +1 plus x minus 3 is equal to 0. So it's +1 minus 3 is equal to minus x. X is equal to 2, essentially +2. So iron becomes +2. So iron goes from +3 to +2. +3 to +2. And lithium goes from +1 to +1. Essentially no change. Write the equation for the overall reaction that occurs when this cell is discharging. Okay, let's find out the overall reaction. This is how you do it. So you need to balance the number of electrons. They are already balanced, 1 electron on each side. You can cancel out the ones on the right and left hand side. If you have like on the right and left side of this arrow, you can cancel them out. In the first equation, lithium plus is on the right. On the second equation, lithium is to the left. We can cancel these out. So what are the remaining things at the left? We have LiC6 and FePO4, right? At the left. So LiC6 and FePO4 on the left hand side. What about the right hand side? We have 6C and LiFePO4. We have 6C and LiFePO4. We have these, okay? So that's how we construct the overall reaction, right? Moving on to question number 3. Explain with reference to the qualitative model of electron pair repulsion, VSEPR theory, right? Valence shell electron pair repulsion theory. Why the IO3 minus anion has a pyramidal shape. Come on, let's try to figure this out. So, we're going to look at the central atom, which is iodine, right? It has 3 bond pairs, okay? The rule for hybridization is you will not consider the pi bonds. Only the sigma bonds or single covalent bonds will be considered. No double or triple bonds, okay? The pi bond won't be considered. So, it has 3 bond pairs basically. Okay. Now, what about iodine? Iodine in general, it's in group 7, right? So, 1 electron is going here, 2 electrons are going here, 2 are going here. So, in total, we have 1, 2, 3, 4, 5. But it's in group 7. So, it still has 1 lone pair left that isn't involved in bonding. 5 of its electrons are involved in bonding, but 1 lone pair isn't involved in bonding. So, it has 3 bond pairs and 1 lone pair. So this combination of 3 BP plus 1 LP, where have you seen this? In ammonia, right? Ammonia has 3 bond pairs, the nitrogen atom, and 1 lone pair. So we get a pyramidal shape, okay? So 3 bonding pair centers and 1 lone pair on iodine. So that's it essentially, yeah. Okay, now the reaction of iodine and hot aqueous sodium hydroxide is similar to that of chlorine and hot aqueous sodium hydroxide. So this is content from AS. You need to have this memorized basically. You know that chlorine reacts with sodium hydroxide under 2 conditions, basically hot aqueous sodium hydroxide and cold aqueous sodium hydroxide. Okay, so when it reacts with hot NaOH, it forms the iodate 5 ion or the chlorate 5 ion basically. Okay, and when it reacts with cold NaOH, it basically forms chlorate 1. Why is it called chlorate 1? Because chlorine has an oxidation number of +1. So you need to have both the reactions memorized, and the oxidation numbers also help you to balance this. Look at this. I have the oxidation numbers given here. Chlorine goes from 0 to -1. It also goes from 0 to +5. So there's a change of 5 electrons over here, and there's a change of 1 electron over here. So to balance things out, you basically need to multiply the one below with a 5. Okay, basically you need to multiply the one below with a 5. I'll show you how it's done. So if you multiply a 5 here, then that means you need 5 NaCl. So in total you need 5 plus 1, 6 chlorine atoms or 3 molecules of chlorine. And how many sodiums? You need 6 sodiums, right? And you need 3 waters to balance things out. So that's how we do it. I don't have it memorized. I just have the products memorized. I don't have the balancing memorized. But you need to know the products, right? You're going to get a NaCl for both of them and NaI here for both of them. Okay, so depending on the halogen, it's just going to change. They told you that you're going to get sodium iodate as one of the products. Okay, moving on. This is a tough one. The decomposition of hydrogen peroxide is catalyzed by acidified iodate. I think I have this done. Wait a bit. Alright, so yeah, I did have it. I just copied it. So let's begin. Let's see what we have here. This question is a bit complicated, okay? So pay attention. For question 3C, use the data. Okay, so we have hydrogen peroxide. The decomposition of hydrogen peroxide is catalyzed by acidified iodate 5 plus 5. Okay, so H2O2 reduces acidified iodate 5. The reaction is followed by the oxidation of iodine by H2O2. All right. So at first, hydrogen peroxide is reduced, and actually at first, iodate. Iodate goes from, what is the oxidation number here? It is plus 5, and it's 0 over here. What about oxygen? Oxygen is minus 1 in hydrogen peroxide, and it's 0 here over here. So oxygen is basically oxidized and iodine is reduced. Afterwards, iodine is oxidized by H2O2. Now here's the thing. Use the data to show that the separate reactions of H2O2 with iodate and with iodine are both feasible under standard conditions. Okay, let's start. Let's look at the first reaction. Okay, the first one being where hydrogen peroxide is oxidized and iodate is reduced. This is oxidation and this is reduction. So hydrogen peroxide is oxidized and iodate is reduced. So let's look at this. The reduction potential of iodate, we're going to take that. We're taking the reduction potential of iodate. That's 1.19. The reduction potential of iodate is 1.19, and the oxidation potential of hydrogen peroxide will be its basically the reverse. Okay, it will basically be the reverse. As you can see, I'm doing the green one first. Okay, let's do this first. I'll make you understand. In this equation, this one given over here, iodate is being reduced. So for sure, we need to take the reduction potential of iodate. And what else is happening? Hydrogen peroxide is reacting with this iodate over here to form oxygen. Okay, and as you can see, we can easily balance these equations. How? To balance 5 and 2, what do we need to do? We need to multiply this equation with 2 and multiply this equation with 5. Then it's balanced. Okay, so I've already balanced it on the right hand side over here. As you can see, look at the green equation. This is the balanced equation essentially. Okay, this one. Let me show you. So we have iodate, right? We are multiplying this by 2. So 2 molecules of iodate, 12 molecules of H plus, 10 electrons. Okay, got it? Then 1 molecule of iodine and 6 molecules of water. On the other hand, for this one, we need to multiply this by 5 and we have to reverse it. Okay, we have to reverse it or else it won't work. So 5 molecules of hydrogen peroxide is being converted to 10 H plus, 5 O2 and 10 electrons. So what can we do now? we can get rid of the 10 electrons on both sides. Okay, so what's the end result? We have 2IO3 minus 5H2O2, right? Then 2H plus remaining. 12 minus 10 is 2. Okay, and on the right hand side we have iodine, 6 molecules of water, and 5 molecules of O2. As you can see, this purple equation matches with this one over here. Okay, so I'm showing you that this is feasible. Why? Because the reduction potential for iodide 5 is plus 1.19, and the oxidation potential for hydrogen peroxide to oxygen is actually minus 0.68. We need to change the sign. So what's the end result? 1.19 minus 0.68 is actually plus 0.51. That's what we are showing here. Okay, we're showing them that the E cell for this half cell, the iodate hydrogen peroxide half cell, is actually plus 0.51, which is actually, therefore, it is feasible. Okay, that's the first equation. Now, use the data to show the separate reactions between hydrogen peroxide and iodate and with iodine are both feasible under standard conditions. Now they want us to show that the second reaction is also feasible. Which one? This reaction is followed by the oxidation of iodine by H2O2. Okay, so now let's see that if or whether iodine can be oxidized by using H2O2. So we have to use different equations now. Right? We have to use different equations. Basically, we want to oxidize iodine now. We want to oxidize iodine to get iodate. We want to oxidize iodine to get iodate. And in the process of doing so, hydrogen peroxide will get reduced. Okay, so we want to oxidize iodine and reduce hydrogen peroxide. So we're going to take the reduction potential of hydrogen peroxide plus 1.77 and the oxidation potential of iodine, which is minus 1.19. So 1.77 minus 1.19, that actually gives you a value of plus 0.58, which is also feasible. And if you guys want, I can show you the equation. To balance this, what do we need to do? Again, 2 electrons into 5 and this into 2. That will balance things. Okay, as you can see, I have the equations here. Look at the pink ones. Hydrogen peroxide into 5, iodine into 2. Alright, this is plus 1.77 and this is the oxidation potential, so it's minus 1.19. So if you do solve this, right, if you add it up, both the left and right hand side, you can get rid of 10 electrons on each side. You end up with this 5H2O2 plus iodine. Okay, now look at this. I'm not using the water over here. Why? Because you have 10 water here, 6 water here. So 10 minus 6 is 4. Similarly, you have 12H plus here and 10H plus here. 12 minus 10 is 2. 2H plus and 4H2 on the right hand side and 2IO3 minus. That's your equation for the oxidation of iodine by using hydrogen peroxide, by reducing hydrogen peroxide. Okay. In your answer, give the equation for the reaction with hydrogen peroxide with iodine. I have given that over here. Okay, with the balancing. I've shown the balancing on the right. Pretty complicated, yeah? 5H2O2 plus I2 is equal to 4H2O plus 2IO3 minus iodate 5 plus 2H plus. That's it. Now, write the overall equation for the decomposition of H2O2 catalyzed by acidified IO3 minus. Okay, come on guys, let's look at the two main equations. Okay, which ones am I talking about exactly? The purple one and the pink one. Why don't I use a different color? I'm talking about this purple one and this pink one. Okay, so look at the purple one. What do we have? 2IO3 minus plus 5H2O2 plus 2H plus is equal to I2 plus 6H2O plus 5O2. What about the pink one? We have 5H2O2 plus iodine is equal to 4H2O plus 2H plus 2IO3 minus. Essentially what you can do is you can cross out things that are present on different sides. Okay, so we can get rid of these two. We can get rid of these two. We can get rid of these two. What do we have left then? On the left hand side, 10 H2O2 is converted to 10 H2O plus 5 O2. So this is what we get after cancelling everything out. You can write this in a simpler form. If you divide everything by 5, 2H2O2 is equal to 2H2O plus O2. So that's it, and that's our final equation. Pretty complex, right guys? It's not that simple. This paper is hard in general. The organic part is even harder. Okay, so see if you get it. If you do have problems, please comment below. I'll try to make you understand. Also guys, if you like the content, remember to subscribe to the channel and like the video. Helps with the algorithm a lot. And please share the video with your friends if they do need help. Moving on to part D. This is a question on orders and rate. Okay. Let's see. Come on. So, order with respect to hydrogen peroxide. Check this out. So, which equations are we going to use? Clearly, okay, this is a bit complicated, right? Okay, we're going to use 3 and 4. We're going to use experiment 3 and 4. Okay. Let me write this again. The answer is first order with respect to H2O2. How exactly? Basically, look at this. In experiment 3 and 4, these have remained constant, and we have increased the concentration by a factor of 1.5 times. Okay, so using experiment 3 and 4, what happened? Change in concentration x 1.5 times. How exactly? 0.150 divided by 0.100 is a change of 1.5 times. Gives increase rate of 1.5 times, as you can see. Okay, 8.82 into 10 power minus 5 divided by 5.88. Try doing this into 10 power minus 5. Use your calculator. 8.82 by 5.88. That's also 1.5. So it's first order with respect to this. Okay, now what about the second one? IO3 minus iodine. So for this, which one can we use? We can use 1 and 3, right? Let's use 1 and 3. Look what happened. H plus has remained constant. Okay, we have doubled H2O2. We have also doubled iodate. Okay, so this is also first order with respect to iodate. Why is that? Because look at this. Since we've doubled this and it's first order, look at the total change. 5.88 into 10 power minus 5 divided by 1.47 into 10 power minus 5. How much is the change actually? That's 5.88 divided by 1.47. That's actually 4 times. So what actually happened? When we doubled it at first, 1.47 into 10 power minus 5 became twice. 1.47 into 2, that's 2.94. This happened after we doubled hydrogen peroxide. Okay, so look at the final one. 5.88 into 10 power minus 5 divided by 2.94 into 10 power minus 5. So 5.88 divided by 2.94, how much is that? That's 2. What did you understand? Basically, we already know it's first order with respect to H2O2. So doubling it will double rate. Now we also have figured out that it is first order with respect to iodate. Why? Because we have also doubled iodate, which caused the rate to double again. Okay, so it increased by a factor of 4 times. Why? Because we have doubled hydrogen peroxide and we have also doubled iodate. Okay, so how are we going to write this? Change in concentration times 2 gives increased rate x2 as reaction is first order with respect to H2O2. Get it? Next, order with respect to H plus. Now this is interesting. How are you going to figure this out? Order with respect to H plus. Okay, let's use 1 and 2, right? It's your choice. You have a lot of options. Look what happened in 1, 2. We doubled rate, right? We doubled the concentration of H2O2. We would expect it to double, and it has doubled. We have also doubled H plus, but nothing happened to rate. That means that it is 0 order with respect to H plus. 0 order with respect to H plus. Why is that? Change in concentration has no effect on rate. So this was done using experiment 1 and 2. And for this, which one did we use? We used experiment 1 and 3, right? So basically, we doubled H2O2. Rate also doubled, right? 2.94 divided by 1.47 is 2. We also doubled H plus, but there was no change in rate. That's it. So use the overall rate equation. Write down the overall rate equation. So it's first order with respect to H2O2, first order with respect to iodate, and 0 order with respect to H plus. So it's K H2O2 IO3 minus. That's it. Now calculate the value of the rate constant using data from experiment 4 and your answer to D2. So we're going to use the data from here. So the rate is 8.82 into 10 power minus 5. Rate is 8.82 into 10 power minus 5. Okay, 8.82 into 10 power minus 5 is equal to K into, what are the concentrations? 0.150 and 0.140. 0.140 into 0.150, and this is the rate. So we get a value of 4.20 into 10 power minus 3. Now here's the thing. The unit of rate will always be mole per dm cube per second. This has mole per dm cube, this has mole per dm cube as well. So if you make K the subject, you're going to get mole per dm cube per second divided by mole square dm to the power minus 6. We're going to get a net result of mole to the power minus 1 dm cube second to the power minus 1. That's all. 4.20 into 10 power minus 3. That's your final answer. Mole minus 1 dm cube second minus 1. Okay. Now, lead iodate 5 is only sparingly soluble in water. Write an expression for the solubility product. Okay. So, if you dissolve lead, it is sparingly soluble. We're gonna get 1 lead 2 plus ion and 2 iodate ions, right? So we're gonna get the solubility product will be Pb 2 plus and IO3. Okay. IO3 minus. That's it. Whole square. Since there are two of them, right? Calculate the solubility product of this. Okay. So here's the logic, right? Try to understand this step by step. So if lead iodate has a concentration of X, since the molar ratio is 1:1 for lead and lead iodate, this will also be X. And since the concentration of iodate is twice that of lead iodate, this will be twice. So this will be 2X, okay? So if we input this over here, this is x, and this is twice x, right? So Ksp is actually equal to x into twice x whole square. Now another thing I want to teach you is uh, this is the solubility product, okay? Now they want the solubility. Solubility essentially means the concentration of lead iodide. They want the concentration of lead iodide. Solubility means concentration. That means they want the value of x essentially. So 3.69 into 10 power minus 13 is equal to, if you break the brackets, what do you get? X into 4x square, which is 4x cube, right? And if you make x the subject, you're going to get 4.52 into 10 to the power minus 5. Okay. Answer divided by 4 cubic root. Basically, what did I do? From here we went x is equal to 3.69 into 10 power minus 13 divided by 4, then cubic root answer. Okay, then we're going to get our answer as 4.52 into 10 to the power minus 5. That is it. Okay, ammonium iodate is an unstable compound that readily decomposes when warmed. The decomposition reaction is shown. Use the data in the table to calculate the entropy change of the reaction. Del S of the decomposition of ammonium iodate. Okay, so it's pretty straightforward. I'll teach you. This is what we do. We have, it's basically product minus reactant. Okay, so the products: water 70 into 2, iodine 261 into half, oxygen 205 into half, nitrogen 192 into half. What about ammonium iodate? That's just 42. So clearly entropy has increased, right? So 261 into half plus 205 into half plus 192 into half. Okay, these are the products minus the reactants, just 42. We're getting a value of plus 427 joules per Kelvin per mole. Plus 427. Okay, the reaction is feasible at all temperatures. Explain why using the data in F and the answer to F1. Interesting. Basically, guys, look at this. This is the equation for Gibbs free energy. You guys know that Gibbs free energy del G is equal to del H minus T del S, right? Now, for a reaction to be feasible, Gibbs free energy must be negative. Now, check this out. The enthalpy change of this reaction is negative, and the entropy change, the change in entropy is also is positive. Okay, but there's a minus sign in this formula before del S, right? So minus plus equals to minus. So in general, this value will be negative. So T del S minus T del S will always be negative, and del H is also always negative. So del G will always have a negative value, and that's the reason. Okay, so that's what we have to say. Del G is always negative. Why is that? Because del H is negative or less than 0, we can say that it's exothermic, right? Or you could say that it's an exothermic reaction. And what else do we have to say? We need to mention that del S is greater than 0, or it's positive, right? Or you could say that basically minus T del S is always less than 0 for all values of T. So that's the reasoning. Okay, hopefully you understood the math. Moving on to 4, we have 4, 5, 6, 7 left. These are the ones remaining. State the meaning of transition element. Let's do this. So a transition element is an element that forms one or more stable ions with incomplete or partially filled 3d orbitals, or you could just opt for a d subshell. Okay, the d orbitals in an isolated transition mineral are degenerate. This means having the same energy level. In complexes, the d orbitals occupy two energy levels. They are split, right? Ligand field splitting. So let's see what happens. In an octahedral complex, what happens? Basically, two orbitals go to the higher energy level, okay? Two orbitals go to the higher energy level. So basically, two up here, and three orbitals go to a lower energy level. On the other hand, for a tetrahedral complex, three orbitals go to a higher energy level, and two orbitals go to the lower energy level. This is the logic. You need to remember this. Sketch the shape of the two d orbitals. One d orbital from the lower energy level in an octahedral complex. Okay, so what about the ones at the top? What are these? These are the dx square minus y square and dz square. So what about these? These are dxy, dxz, dyz. Okay, one d orbital from the lower energy level in an octahedral complex. So it's either dxy, xz, or yz. Any one of these will work. So why don't I draw dxz? So these orbitals are actually between the x. Why don't I draw dxy? Okay, I'm drawing dxy. These are actually in between the x and y axes. Okay, so dx and y, it's like this basically. Okay, essentially it's between the axes. Sorry, between the axes. So yeah, here it's between the x and y axis. We had an alternate route for the lower energy orbital. You could go for xz maybe, but it's a bit tough to draw. You could draw dyz as well. dyz is like this. Dyz. This is dyz. Okay. Suppose this was dyz. Okay, that's another lower energy orbital. All right. So you can draw any one of those three. What about the higher energy orbital in the octahedral complex? Either dx square minus y square or dz square. So dx square minus y square is literally like this. It's like a p orbital, but it will pass through, right? It will pass through the axes themselves, okay? It's like the combination of a px and py orbital, right? This is the dxy orbital. What about the dz square orbital? If you wanted to draw that, that's another option. It's basically a p orbital passing through the z-axis, and then what do you need? You need a halo. Basically, you need a halo that's like this, passing through the x and y axis. This is the dz square orbital. Okay, I've drawn all of them for you more or less. Okay, now moving on, let's go to the next one. On the diagram of ED ds 4 minus, circle each atom that forms a bond to the Fe3 plus ion. Okay, these are polydentate ligands. Basically, anything with a lone pair can form a bond. Okay, so ammonia, you know that nitrogen has a lone pair, so it can form a bond. By the way, these oxygens, all of them can also they also have lone pairs. Okay, so they can also form bonds. All right. So if we want more accuracy, this is what you can do. Since they told us to draw circles around the atoms, right? So we actually need to circle these atoms over here, the nitrogens and these oxygens per se. That's it. Next, one is red and the other is yellow. Why do they have different colors? Okay, the main reason is basically you saw this gap that I drew between the split orbitals. Basically the gap varies from complex to complex. Okay, so the dd energy gap, or basically del E, is different for complexes, for both of these complexes, right? So we can say that a different frequency or wavelength of light is absorbed. Okay, always remember the color we see is the wavelength that is not absorbed. Complementary of the color that is absorbed. Okay, so suppose if out of RGB, if you absorb red and green light, you will be seeing a blue, color. Okay, there are other variants where there are questions based on this. What's the process of seeing colors? I'll also be doing those variants. Okay, I'm going to focus on chemistry for the next few days. Let's see where it goes. State the type of reaction that occurs. When one ligand exchanges the place of another, it's called a ligand exchange reaction. It's a ligand exchange or substitution. Okay, or displacement or a replacement reaction. Anything works. Expression for the stability constant of FeEDDS. Okay, basically we're going to use this. Product by reactant, always remember. Okay, and water molecules do not take part in the K-step equation. Okay, so let's begin. We have FeEDDS minus by FeH2O6 3 plus, just like this. FeH2O6 3 plus, and what else? By the way, there is another complication, that is, as you can see, the charge is given outside the bracket here, but okay, hear me out. Basically, in stability constants, the issue is you cannot give the power out of the brackets, because the powers actually refer to the number of ions present in the equation. Since there is only one iron 6, basically iron H2O6 compound, and 3 plus present here, we cannot give the 3 outside. If there were 3 present, we could use 3. And what about EDDS? There's only one molecule of EDDS present as well, right? So we can just use one EDDS. We cannot give the power 4 minus outside. It has to be kept inside the bracket. Okay, so that's EDDS 4 minus, then third bracket. Remember that. The table shows the value for the stability constants of both complexes. Clearly, this is much more stable, right? Predict which is more stable. So it's FeEDTA. So FeEDTA minus is more stable, as it has the higher K-step. Okay, that's it. When an excess of EDTA 4 minus is added to the FeEDDS complex, the following equilibrium is established. Okay, calculate the equilibrium constant for this equilibrium using the K-step values given in the table. Interesting. So check this out, guys. Basically, the equilibrium constant that we need to figure out is EDDS 4 minus into FeEDTA minus divided by FeEDDS minus into EDTA 4 minus. This is what we need to find. Okay. Now, how are we going to do this actually? We need to tread carefully. We have one of the K steps already. This is the stability constant for, this is the K step, right, for FeEDDS. Okay. What about the other one? Do we have the K step for EDTA? Have I written that down? I haven't, right? But basically it will have a similar one. It will also react with water, and it will exchange the water molecules similarly. Okay, I can write an equation for that. Basically the equation will be like this. Suppose iron H2O6 3 plus will react with one molecule of EDTA 4 minus to form FeEDTA, okay, FeEDTA just minus and 6 molecules of water. Now if we write down the case tab, right, the case tab for FeEDTA, this is so annoying, right, is going to be basically FeEDTA, you cannot get the minus outside here, okay, divide by EDTA 4 minus into FeH2O6 3 plus. Okay, so these are the two that we have, the stability constant for EDTA as well as the stability constant for EDDS, the complex with EDDS. Now, this is how I do it. Usually it's a multiplication or division. Okay, now you need to figure out whether it's a multiplication or division, and if it's division, which one will go on top. How to do this, okay? Just look at the numerators. For the complex of EDTS, look where the numerator ends up at. It goes to the denominator, right? What does that indicate? This must be at the denominator side, okay? What about this? Look at the numerator for this, for EDTA. It remains at the top. What does that indicate? This is clearly the numerator. So I am suspecting that it should be like this. The Kc should actually be the case tab for FeEDTA minus divided by the case tab for FeEDDS minus. This is what I'm suspecting. And let's see if it matches. Come on. So case tab for EDTA. I'm gonna copy this. Wait up. This divided by this over here. Okay. If you do this, check this out. We can get rid of these two. And after reciprocal, what do we end up with? FeEDTA minus, after reciprocal, EDDS4 minus divided by FeEDDS minus into EDTA4 minus. See if it matches. It is totally perfect. It matched with this over here. So this is the correct answer. Okay. So Kc is equal to case tab of EDTA divided by the case tab of EDDS. Okay, that's actually 1.26 into 10 to the power 25 divided by 3.98 into 10 to the power 20. Where did I get this? From the information over here. Sorry, we're gonna get an answer of 3.17 into 10 to the power 4. Okay. We need a minimum of 2 significant figures, but I'm going to give 3 because I use 3 here. Alright, that is it for question number 4. Now we have 5, 6, and 7 remaining. Let's do this. We won't take that long. Come on. So 5. Carboplatin and cetraplatin are used as anti-cancer drugs instead of cisplatin. Okay, interesting. Describe the action of cisplatin as an anti-cancer drug. You need to know this, okay? Basically, transplatin cannot act as a anti-cancer drug. Okay. I'm going to show you what cisplatin is actually. Check this. This is basically cisplatin, okay? It would have been trans if, you know, for example, this is cis, okay? But we don't want cisplatin. Sorry, we don't want transplatin. We actually want cisplatin, right? So ClNH3, NH3. Describe the action of cisplatin as an anti-cancer drug. Let's go. So basically what it does is cisplatin can bind or binds with DNA or binds with the nitrogenous bases A, T, C, G, etc. Now, which prevents replication of the DNA or the strand. Okay, this is basically what it does. A cancer basically is a cell which has continuous division in mitosis. Basically, we cannot control its mitosis. There was an alternate answer. You could say that it prevents cell division or prevents mitosis. So this is basically your this is the point that you need to say. This is an alternate point. There is another alternate point. What is that? It prevents transcription and formation of mRNA. You don't need these. These are for bio students, basically. Okay. All right. So suggest the geometry of the platinum center in the carboplatin complex. So we're talking about this cisplatin, carboplatin, anything that looks like this. This is clearly square planar. Okay. Square planar. Next, suggest why carboplatin does not show cis-trans isomerism. Okay, so for cis-trans isomerism, the ones I've showed you just now, basically you need these to be able to exchange their places. Understood? But look at carboplatin. Since this is a ring compound, ring compounds cannot show cis-trans isomerism. Mainly because look at this. Yeah, you can change the position of this. You can bring this over here, right? But look at this. If you try to bring this end over to this end, since it's connected to the other end, it wouldn't budge. It's really hard to move, basically. All right, like you can only put it in this orientation, or you could only put it in this orientation. Both oxygens would have to be here, basically. Okay. As a result, it doesn't really make sense. Yeah, so it's not possible. So how are we going to write the answer exactly? They accepted these, the distance between two coordinating oxygens is too small to bond trans. Basically, the trans isomer is not possible. You know, you cannot move this one over here because the distance is too small between them. Or you could go for an alternate answer. Atoms in bidentate ligand can only bond 90 degrees, okay, not 180 degrees. This is another answer. Okay. They can only bond 90 degree, not 180 degrees. Basically they can only bond 90 degrees. Okay, this one is 90 degrees. They cannot bond 180 degrees through this straight line. This is the answer. Understood? Remember that, guys, please. Satroplatin is a neutral complex containing the ligands ethanoate and C6H11NH2 Cl-NH2. Reduce the oxidation state of platinum in satroplatin. Okay. So ammonia and this complex, they don't have any charges. Okay. Each chloride has a charge of -1. Each oxygen each COO2 minus, okay, each chloride has a charge of -1. Each CH3 ethanoate ion also has a charge of -1. So in total, the net charge is -4. So the charge of platinum should be +4. That's it. Compound M is made from 1,3-dimethylbenzene, a two-step process. Okay. Basically, we're making an acyl chloride, right? So what do we need to do? Mainly, how do you convert it to an acyl chloride? We need the carboxylic acid first. Understood? So how are we gonna get the carboxylic acid? For benzene compounds, regardless of the length of the side chain, you can oxidize it using potassium permanganate. Okay. So regardless of the length, you're always going to get benzoic acid. So the structure of L should be like this. Or you could opt for this. Get it? Now, what next? The condition for step 1 is heat under reflux, or just heat reflux with acidified or alkaline KMnO. If you opt for alkaline KMnO4, then you have to say then acidified. It's not necessary. Just go for acidified. That's the best, you know. Then what about step 2? To convert carboxylic acid to an acyl chloride, you can just react with PCl5 in room temperature or SOCl2 in room temperature, or heat with PCl3. Really important, okay? Write an equation for step 2. Let's do this. I'm writing an equation for step 2. Depending on the reagent, it will change. For example, for PCl5, what do we have? We have C8H6O4, right? C8H6O4. Essentially what's going to happen is we're going to lose these OHs and they're going to be replaced by Cls, right? So we're going to lose two OHs, or we're going to lose O2H2, right? We're going to lose O2H2 from here. So if we react it with PCl5, for each carboxylic acid group we're going to need one PCl5. We are going to get C8H4O2Cl2, okay, plus 2 phosphoryl chloride POCl3 and 2 HCl. This is it. If you want another equation, let me show you this. Let me show you this way. COOH COOH plus 2 PCl5. Look at this. This is what's going to happen. We are going to end up with this COCl COCl like this, right? And we're going to get 2 POCl3 and 2 HCl. This is what happens essentially, okay? So these are removed from the compound, these two. There were some alternates if you wanted PCl3, right? You could opt for this C8H6O4 plus 2 SOCl2. Best way to produce it, C8H4O2Cl2 plus 2 SO2 plus 2 HCl. Or there's another option, 3C8H6O4 plus 2 PCl3, 3C8H4O2Cl2 plus H3PO3. To balance this, I think we need a 2 here. So yeah, balancing this is a bit more difficult. How to balance it? Check this out. This is probably the way. First, you need to think about the chlorines. To balance the chlorines, you need a 3 here and a 2 here, right? To make it 6. Now to balance everything else, we need a 3 over here and a 2 over here. Okay, this is the logic. Now, a student investigates a possible synthesis of M directly from benzene using COCl2. Okay, directly from benzene using COCl2. We want this essentially. Get it? That's what do you know that as? That's Friedel-Crafts acylation, right? That's possible. Benzene initially reacts with COCl2 as shown. Oh, COCl2, yeah, in the presence of AlCl3 catalyst, right? So it's a two-step reaction. We get an intermediate, right? This total mechanism is electrophilic substitution. Reaction 2 is electrophilic substitution of Cl, C plus O for H plus in benzene. Suggest the mechanism for reaction 2. So they want us to draw the mechanism. Okay. So essentially what happens is AlCl3 is acting as the catalyst. How exactly? Mainly AlCl3 helps in the formation of the electrophile. It takes one chloride away from COCl2, so we end up with COCl plus. That's what we end up with. Now the electrophile can attack the nucleophile. Okay, so hear me out. We have the benzene ring over here and we have the electrophile over here. That means we have COCl over here. This is our electrophile. it's going to attack the benzene ring. Okay, so arrows. Even though the electrophile is attacking the nucleophile, the arrows always need to be drawn from the nucleophile to the electrophile, and the arrows must always be curly. Remember that. So arrows from nucleophile to electrophile. Now what we are going to have our intermediate, right? With the lunar shape. It needs to cover 5 carbon atoms. So we're gonna have COCl over here and the hydrogen over here as well. Okay. And to make the compound, there will be heterolytic fission of this bond, and we're gonna get our final compound, COCl plus H plus this. But listen, it's not the end because we need 2 COCls, right? It's not over yet. But yeah, that's it. This is just getting one of them, right? One of the groups. So it's not actually a direct reaction. We still need more time. So it's not over yet. Now for 6, last 2 questions. Fumaric acid is a naturally occurring dicarboxylic acid. Identify the products of the reaction between fumaric acid and an excess of hot concentrated esterified pancreatine. Okay, so you know that for an alkene, oxidation of alkenes, if it has one alkyl group, you're gonna get a carboxylic acid. Okay, so this compound is, we're gonna get 2 compounds essentially, CO2H, CO2H on the left hand side, and here we're gonna get, this compound was basically this CO2H, CH. If you break this down, you're gonna get 2 CO2Hs. Okay, similarly CO2H over here, CO2H over here. Now what is the name of this compound? This is ethane dioic acid. 2 compounds are unstable in the presence of hot KNO4, ethane dioic acid and methanoic acid. They are further oxidized. Oxidative cleavage of those compounds occur and they form carbon dioxide and water. This is really important. Okay, so the correct answer should be carbon dioxide and water. If you wrote these, you would get 0 marks. Okay, fumaric acid can form addition and condensation polymers. Repeat unit for addition polymers. Okay, so this is a trick. Basically draw it straight in a straight line like this. Okay, next hydrogen over here, CO2H over here, similarly hydrogen over here, CO2H over here, and yeah, we're gonna have a dotted line like this. Repeat unit. Draw the repeat unit of the polyester formed when fumaric acid reacts with ethane 1,2-diol. Okay, so we have CH2OH, CH2OH. This is ethane 1,2-diol, and we have fumaric acid over here. So we want to form a polyester. Okay, CO2H, CH double bond, CH, CO2H. Okay. Let's form polyester. So the polyester will form between the alcohol group and the carboxylic acid group, right? Let's do this. Carboxylic acid group and the alcohol group. So come on, I'll show you 2 ways of drawing it. This is one way. Suppose CH double bond CH, CO, CO. Okay, here we're going to show the ester bond as O, COO, right? Then we have CH2, CH2O, dotted line. This is one way of drawing it. Okay. The alternate way is the skeletal. Let's draw the skeletal now. Okay, so skeletal will be like this, same thing but just skeletal. So for example, if I draw it like this, double bond over here, here you go. This is another possibility basically. This is the fumaric acid section and this is ethane 1,2-diol section. Okay, moving on. Explain when polyesters normally biodegrade more readily than polyalkenes. It's pretty simple. You guys know that they can be hydrolyzed, right? So polyesters, or you can say that they can be broken down by a hydrolysis, or you could say that C-C bonds are non-polar or polyalkenes. Remember that polyalkenes cannot be hydrolyzed. Okay, that's all. Fumic acid reacts with cold diode KMnO4 to form this compound, a diol. Okay, only 3 stereoisomers of P exist. One of the stereoisomers is shown. This is quite interesting. These questions are very rare. Let's try to understand. So the trick is, look at this. They've already given you the position of this, so they've made this easier. Mm, let's try doing this. To make things easier, I'm going to teach you a trick. What we can do is, we can keep the COH groups, the carboxyl groups on the same plane. Understood? I've kept them on the same plane. This is the same plane. Now, let me try to make you understand. How can we form an isomer? Stereoisomers. Stereoisomers refer to atoms like same molecular formula and structural formula, but different arrangement of atoms in space, different spatial arrangement of atoms. Look at this. The OH group is above the plane of carboxyl, right? And the OH group is also above the plane of carboxyl here. On the other hand, the hydrogen atoms are below the plane, below the pink plane. The dotted line means that it's below the plane. The bold line means that it's coming out. Okay. So we cannot draw this. So why don't we just mix things up a bit? Why don't we just mix things up? What if I keep one OH at the top, right? And H at the bottom. But here I can bring OH down to the bottom and H above. So this is one isomer. Because look at this. Here one OH is above and one OH is at the bottom. Now I'm going to draw another alternative to this. You could exchange the positions of these. Like keep H at the top over here and OH at the bottom. And similarly, OH could remain at the top here and H could be at the bottom. These two that I've drawn, they are the same isomer actually. You guys need to understand this. Because look, one OH at the top, one OH at the bottom. One OH at the bottom, one OH at the top. Same thing. Similarly, one H at the top, one H at the bottom. One H at the top, one H at the bottom. That's the logic. So they're actually the same compound. Okay, so what's the other one? What's the different compound? What if here both the OH were above the plane, right? What if I bring both the OHs below the plane? Now I have another different compound, right? This is different because both H's are above the plane and both OH's are below the plane. That's it. It's a bit complicated, yeah? Now for D, enzymes are not in our syllabus anymore from 2020 onwards, so I'm going to skip this, okay? Moving on to our last question. This is a bit complicated, question number 7. Find the last one. It's been a long time since I've started recording. It's been 1 hour 25 minutes already. Takes a lot of time to solve chemistry paper force. Okay, let's begin. Proline is a naturally occurring amino acid, right? Proline is often found bonded to glycine in a protein. Draw the peptide progly. So this won't be in the, you won't have the data booklet anymore, but listen, in the data booklet you basically have the R groups of amino acids, okay? So if you go to the end of the data booklet, you're gonna find that glycine is the simplest amino acid with an R group of hydrogen only. That's literally it. Yeah. So proline, glycine, progly, right? So you have two options. You can either form this, like this is glycine essentially. C H H COOH and NH2. So you can either form the peptide bond between this group and this group over here, which is the one I've done here, or there's another alternative. We can form a bond between the COH of this group and the NH of proline. Get it? So let's do that. Come on. Okay. OH. Now with this N, we're gonna get rid of the hydrogen, and we're gonna form this over here. CH2, NH2. This is it. Okay, and if you want the skeletal answer, the one they've given in the mark scheme, it goes like this: C double bond O, CONH. We don't have the N H actually. It's like this. All right. Hopefully you get it. Understood? Name the type of reaction that forms a dipeptide between two amino acids. That's the condensation reaction. We lose one molecule of water in doing so. Now, proline is able to form polyproline peptide chain. A section of the polyproline is shown. Suggest why the secondary structure cannot be stabilized by hydrogen bonding. Okay, remember, hydrogen bonding is present in the secondary structure of proteins between the CONHs of the compound. So for hydrogen bonding, you need three elements basically, NOF, and you need a hydrogen attached to any one of them. So we do have nitrogen, right? And we do have oxygen, but we don't actually have a hydrogen attached directly to them, unlike progly. See, here we had a hydrogen attached to nitrogen. That's why it could be progly could be stabilized by hydrogen bonding, but not polyproline, because the nitrogen does not have a hydrogen linked to it directly. Understood? By the way, there was an alternate option for this. You could also opt for substitution or addition elimination. Okay, but just go for condensation is the better answer, right? Okay, let's go to part B. Come on. Part B. For part B, the reaction scheme shows several reactions of proline. Okay, so proline reacts with an acyl chloride to form an amide. It reacts with the NaOH to form a salt, basically the carboxylic acid section. And we also have a reaction 3 where the carboxylic acid actually turns to an alcohol group. So what is that basically? That's a reduction reaction. Okay, so they want the equation for reaction 1. Okay, so NaOH will basically react with this carboxylic acid group, right? What does this section give us actually? It will actually turn into RCOO minus Na plus, and we're gonna get one molecule of water, right? Basically this and this will combine to form one molecule of water. So C4H7N4 CH2H plus NaOH. This section remains unchanged actually. We can call this the R group. Okay, so C4H7 NHCOO minus Na plus plus H2O. They've actually written it in this way. They've written it as C4H7CO2Na plus H2O. But COO minus Na plus is better. Anything works really. It's fine. Your wish. Proline has a secondary amine functional group. Secondary amines react with acyl chlorides. For example, diethylamine reacts with RCOCl according to the following equation. Okay, to get an we get an amide basically, a pseudoamide, because we don't actually have the hydrogen attached. Suggest the skeletal structure of R, the product of reaction 2. Okay, so when proline reacts with let me draw it for you guys. We have proline over here. Now it's going to react with CH3COCl, right? CH3COCl. When it's going to react, what's going to happen is basically we're going to get rid of the hydrogen, and you know CH3COCl. Do you see this chlorine section? It will actually react with this hydrogen to form HCl. Okay, and what else is remaining? The CH3CO section is remaining at the end of the reaction, right? So what's going to happen is basically the CH3CO will be connected with the with this section over here. Okay, that's basically it. So one sec, it's gonna be like this: COCl. This is the compound that we're getting. Sorry, COCH3, like this. Okay, so they want the skeletal structure for this, right? Skeletal structure. So yeah, it's gonna be just like this. You're gonna give a nitrogen here. You have this over here, right? And here it's gonna be like this. Here, this is the skeletal structure, right? Now suggest a reagent required for reaction 3. I was telling you guys, reaction 3 is a reduction reaction. So the carboxy acid group is converted to an alcohol. The only suitable reagent for this is lithium aluminium hydride. Okay, LiAlH4. It's a reducing agent. Next, proline was first synthesized in the laboratory using a multi-stage synthetic route. In stage 1, CH2, CO2, C2, H52 and CH2 double bond CHCN react to form a single product. So name the functional groups present in the reactants in stage 1. In stage 1, this is our compound basically. This is the compound, okay? Here. CH2, C, 2 hydrogens and 2 groups of CO2, C2H5. CO2, C2H5, okay? Now the logic is, what are the compounds present? Clearly we have an ester group, right? Here, we have an ester group. We have 2 esters, so we can call it a diester. Okay, even if you didn't write di, you would still get full marks. It's fine. You could just write ester. What about this compound? We have an alkene here and we have a nitrile group here. Okay, so alkene and nitrile. They accepted cyanide, but from 2022 onwards, they don't accept cyanide anymore. Okay, call it nitrile, not cyanide. So just a type of reaction that occurs in stage 1. Okay, so what's happening here? Check this out. This section remained unchanged. This section remained unchanged. Okay, so what changed actually? The hydrogen remained unchanged. This part changed, right? What happened was, from 2 reagents we got 1 product, right? So basically it was an addition reaction, right? That's it. It was an addition reaction. The hydrogen in our compound, it was actually added to CH2. Hear me out. CH2 CHCN. We had 2 hands, right? So this hydrogen basically was added here, and our carbon, right, it formed a bond with this CH2 over here. As a result, this is the end product, the one that we're getting. We had this, right, CH2 double bond CHCN. So we're going to remove the double bond, right, and there was a hydrogen over here. We're going to remove this hydrogen. What's going to happen is this carbon will form a bond with this carbon over here, and the hydrogen that we had residually will go over here. So we're getting CH2 CH2CN. It's an addition reaction basically. Okay, in stage 2 you react with reagent V to form W. What's happening here? The nitrile is converted to an amine. This is also a reduction reaction. We can use in the syllabus, they've mentioned lithium aluminum hydride, but in the mark scheme it's not given. If you gave LiLH4, it's fine, you would get full marks. What are the alternatives? Hydrogen plus nickel, or you could opt for hydrogen plus platinum, or you could opt for hydrogen plus palladium. All of them work, okay? Other than that, you can use hydrogen plus nickel for a reduction of the benzene ring or alkenes. Stage 3 takes place in the presence of an acid catalyst. X and Y are the only products of the reaction. Okay, so what's happening? We're getting a cyclic compound, right? So as you can see, guys, this one of the parts remained unchanged. This hydrogen also remained unchanged. We haven't shown it because it's a skeletal compound, but it still exists. So what has changed really? So this part has actually reacted with this part, right? Okay, essentially that's what happened. And we got a compound Y. Okay, so a small molecule was released in the presence of an acid catalyst. This looks like esterification, right? Since we got, or amide formation. This happened in the presence of a catalyst. So what happened was this NH, right? this NH actually bonded with, let me draw it for you guys. See this. So this is our compound, right? CH CO2 C2H5, and we have COO CH2 CH3. Okay. So look at what's happening, right? So you see this N over here? This N actually bonds with this carbon over here. Okay, and what is lost in the process of doing so? As you can see, this NH2 turns into NH, one of the hydrogens is lost, and we have the CO section. What happens to the rest of it? This part is lost. Okay, so we lose the OCH2 CH3 part and the hydrogen part. Okay, so we're losing two things. From NH2 we are losing hydrogen, and from COOCH2 CH3 we are losing OCH2 CH3. So if you combine these two, what are we getting? CH3 CH2 OH. That's why we're getting ethanol. Now this was a really hard question, right? You need a lot of IQ to figure this out. Okay, moving on. It never ends. You don't have much left though. After several stages, Z is produced. Okay, cool. In the final stage of synthesis, Z reacts via nucleophilic substitution mechanism to form proline. Complete the diagram to describe the reaction mechanism of the final stage. Draw curly arrows, ions and charges, partial charges, and lone pairs on electrons as appropriate. Draw the structure of any organic intermediate ion. Come on, check this out. So, here what's gonna happen is nitrogen has a lone pair, right? We want to form this compound, proline. So, this nitrogen is gonna form a bond with a certain carbon atom. Which carbon atom? Look, this nitrogen is forming a bond. We're going to turn it into a cyclic compound. It's going to form a bond with the carbon atom that is next to CO2H. Okay, we're going to form a bond with the carbon atom that is next to CO2H. So this carbon over here essentially. Okay, so this nitrogen is going to be attacking this carbon atom over here. But if that does happen, that carbon atom will have 5 bonds. We can't have that, right? So we need heterolytic fission of that bond to occur, and we're going to get a chloride anion sooner or later. Okay, and for this to happen, obviously we need the presence of dipoles. This will be del plus and this will be del minus. Okay, that's the logic behind this. So for our intermediate, we will actually have a chloride anion, right, with a lone pair. We'll actually have a chloride anion. This is our intermediate. We haven't shown they don't want the chloride anion for some reason though. Okay, so what are the marking points? We need the lone pair or an NH2. We need a curly arrow from N to the carbon of CCl. We need the correct dipole on CCl, and we need the curly arrow from CCl to chlorine. Okay, those are 2 marks. Next, for the intermediate, you had 2 options. You can either draw this orange one. Okay, after heterolytic fission of this bond occurs, we get a cation, right? Afterwards, this lone pair will attack that to form the double bond. Or you had another option. This is your other possibility for the intermediate. You could draw this. So what's wrong over here? Basically, hear me out. This nitrogen has 2 hydrogens, right? But it has a deficiency of electrons. Why? Because remember, there was heterolytic fission of this bond, right? So this chlorine actually took both the electrons from this shared covalent pair over here. As a result, a deficiency results here. Now what happens is actually, since this nitrogen will form a bond with this carbon over here, it will actually donate its electron to carbon to fill up that deficiency. But in the process of doing so, this nitrogen will get a positive charge. Now to fix this, what does it do? Basically, a heterolytic fusion of this bond will occur, and we'll get rid of this H. It will turn into H plus, and we'll get our final compound, proline. Now, if you're smart, you can correlate things. This H plus will combine with that chloride ion to form HCl. Okay, so that's the gist of it. So you had two options. You could either draw the pink one or the orange one. Okay, hopefully that makes sense. This was a really hard one. Okay, so even if you couldn't do this, you would still get an A star. Okay, these are extremely difficult for you guys. You need to do a lot of question papers to be able to understand everything or guess it the first time you're doing it. Okay, so everything will not be seen. You need to infer a lot of things, right? Now identify with an asterisk the chiral center in proline. Okay, so this is our chiral center, right? It has 4 different groups attached, 1 hydrogen and 3 different groups. Okay, now, identify the number of amino acids in the structure shown. Check this out. The goal is to identify all peptide bonds. I've labeled them with a square, all the peptide bonds. 1, 2, 3, 4, 5, 6, 7, 8. All CONs or CONHs are peptide bonds. Now, what about the amino acids? Between the peptide bonds, amino acids will exist, okay? So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Let me show you again, okay? Clearly one of the hardest papers, the SmartShep 2021. So this is amino acid 1, right? In between amino acid 2, this ring 3, this long compound, right? 4, then this is 5 in between, this is 6, this ring 7, this one in the middle 8 glycine, this is 9, okay? So there are 9 amino acids in total. At pH 6.5, proline exists in aqueous solution as a zwitterion. A zwitterion is basically a compound which has both a positive and negative charge simultaneously. Okay. Now let's see. How did this come to be actually? Check this. So originally we had proline. Okay. So what happens when a zwitterion is formed? If you guys want to know, basically the COH actually donates its proton and it turns into COO minus. Okay, this turns into COO minus, and on the other hand, it donates the proton to this NH, which has a lone pair, right? As a result, using that lone pair, it can actually accept that proton, and it gets a positive charge because it accepted a proton. So the proton from COH is transferred to the amine. All right, the proton or H plus from COH from carboxylic acid is transferred to amine. That's it. Moving on to 2. The isoelectric point of an amino acid is the pH at which it exists as a zwitterion. 3 of the amino acids in gelatin are proline, alanine, and glutamic acid. Their isoelectric points are shown. Okay. Six, 6.5, and 3.1. So, guys, we're going to perform electrophoresis. A mixture of these amino acids was analyzed by electrophoresis using a buffer solution at pH 4. Draw and label 3 spots on the diagram of the electropherogram to indicate the likely position of each of these species after electrolysis. This is important. Come on. Let's try to figure this out. How I did this, why it happened. Let's see. Basically, guys, remember, we are going to observe these at pH 4. So, below the isoelectric point, it's more acidic than usual, okay? So remember that below the isoelectric pH, your compound will have a positive charge. Why? Because there are excess H plus. Okay, so below isoelectric pH, there are excess H plus ions. So all of the NH2s will exist as NH3 plus. All of the COO minus will exist as COH. So net charge positive. Now above the isoelectric pH, right, we have a deficiency of H plus. So all the NH3 plus will turn into NH2s and all the COHs will turn into CO minus. So we have a net negative charge. Okay, so out of all these, glutamic acid has an isoelectric Okay, so we're using a pH of 4, right? Now, for glutamic acid, the pH used is above the isoelectric point, right? So it will exist as it will have a net negative charge, okay? Because there is a deficiency of H plus, glutamic acid will 4 is comparatively a higher pH compared to its isoelectric point. So glutamic acid will try to fix that. How? It will try to fill up the deficiency of H plus by donating protons, and in doing so these COOHs will become COO minus, and the NH2 will remain as NH2. If it was NH3 plus beforehand, it would turn into NH2. So it has a net charge of 2 minus. Okay, what about alanine and proline? Check this out. So both of them have an isoelectric point which is like above the pH used, pH 4. So this is more acidic than their usual isoelectric point. So there's an excess of H plus. So what will happen exactly? CO2H will remain as CO2H. This NH will turn into NH2 plus. This NH2 will turn into NH3 plus. Okay, so both of them will have a net positive charge of plus 1. Now, after electrophoresis, since proline and alanine are positive, they will move towards the cathode, negative electrode, and glutamic acid will move towards the anode. Now, we will write that down, okay? So, we're going to say that glutamic acid, okay, glutamic, I wrote the short form. So, glutamic acid moves towards anode. Why? It moves towards anode, or you could say that it's the positive pole, as it is negatively charged, right? Or you could say that as it contains COO minus, or 2 COH minus, it doesn't really matter. And on the other hand, you could also say that mm, proline or alanine in general move towards the negative pole or cathode, as they are positively charged, or they got as it contains NH2 plus for proline, and for alanine it contains NH3 plus. Okay, so these will give you the same marking point. Okay, so what's the mark distribution for 4 marks? Basically, 1 mark for the glutamic acid, like why they're moving towards the positive or negative pole in general. Look at the second mark. It's for the explanation why alanine moves further. As you can see, alanine moves further. So in electrophoresis, the distance traveled depends on two factors: size and charge. Both alanine and proline have the same charge, plus 1. Why does alanine move further? Because it has a smaller mass. Okay, so we're going to write that Ala moves farther than proline because of lower MR or size. That's your answer. And the other 2 marks are for a correct diagram. Okay, lower MR or size with positive charge. Okay, the other 2 marks are for a correct diagram. So yeah, you need a lot of you need good understanding to answer these. Okay, that's all. Last one. This is also really hard, part F. No wonder A was at 53. This was like clearly one of the hardest papers, right? Similarly, March 5th, 2022 was also very hard. Okay. Chemistry paper 4 is hard in general, so you can't be expecting much unless you know everything. Okay. So I'm going to try to do May June 2021 as soon as possible, followed by October November, and I'm going to do May June 2022 as soon as it comes out. Yeah. Okay, so let's check this out. ACEs, the weak acid ACEs is a compound that can be used to make a buffer solution for electrophoresis. Okay, so what does a buffer contain? It either contains a weak acid and its conjugate base, or a weak base and its conjugate acid. Okay, these are the compositions for buffer. The anion of the sodium salt of aces is a strong base. Okay, cool. A buffer solution is prepared by the following steps. Check this out. 3.5 grams of C4H9N2O4 SNA is dissolved in 100 cm cube of distilled water. 50 cm cube of 0.2 mole per dm cube dilute hydrochloric acid is added to the solution. Okay, so initially we had the salt, aces. It was dissolved in distilled water to form a solution of aces. Now we added dilute hydrochloric acid to the solution. Okay, so what will happen? As we know, the anion of the sodium salt aces is a base. That base will react with acid, right? A neutralization reaction will occur, but one of it is in excess, right? Let's see what the math is. The resulting mixture is transferred to a 250 cm cube volumetric flask and the solution is made up to the mark. So HCl reacts with aces in a 1:1 molar ratio. Okay, calculate the pH of the buffer solution formed at 290 Kelvin. Let's start this. Ready? So let's find out the initial moles of aces or the base. That's basically what's the mass of the base or the salt. 3.5 grams divided by the AMR 204.1. That's 0.017148 moles. Okay, now we want to find out the moles of the acid added. That's we're going to use these 50 divided by 1000 into 0.2. That gives us an answer of 0.0100 mole. Okay, now check this out. Here I was talking, okay, let's talk about this later. So guys, this is the, wait, yeah, so this is the reaction between the acid and base. They react in a 1:1 molar ratio according to the question. We had 0.0100 mole of acid and 0.017148 moles of base initially. Okay, now what happened after reaction? What actually happened? Okay, so clearly the base was in excess, right? The base was in excess. So after reacting the acid and base in a 1:1 molar ratio, what's going to happen? All the acid will react with the base, but some base will be left remaining. How much? 0.017148 minus 0.0100. If you subtract that, you're going to get an answer of 0.007148. Okay, so that's what we end up with. Now this was before the reaction and this is after the reaction. Before reaction we had acid and base. After reaction we did not have any acid left. All the acid was used up. We had a bit of base remaining, 0.007148, and we had produced some salt and water. Okay, we had produced some salt and water. Water isn't important over here. Okay, so basically they've told us that this base is strong, right? So obviously if a base is strong, its conjugate acid is going to be weak. So what's the composition of this buffer? The strong base, the anion of aces, right? And the strong base and the weak acid or the weak salt that's formed. Okay, so if we consider the base, right, to be strong, its conjugate acid must be weak. That's the logic. Okay, or you could think of it this way. Yeah, like, yeah, it's fine. This is totally fine. So the anion of aces is the strong base and its conjugate acid must be weak, and they form a buffer solution overall. Okay, so a buffer can be composed in, like, can be made in two ways. You can either have a weak acid and its conjugate base which is strong, like this example, or you could have a strong acid and its conjugate base which is weak. Suppose you could have a hydrochloric acid which is strong and conjugate, like, base which is weak, like ammonium hydroxide or something. Okay, now after finding the moles of acid, you could find out the equilibrium amount, like the one I wrote as after reaction, the equilibrium amount of base left, that will be 0.017148 minus 0.0100, which is 0.007148, right? Now, um, that's the base, right? We also need to write something else, the equilibrium amount of aces. Okay, so this is what they want in the mark scheme. I'll show you. And there are two ways of doing this math. Okay, wait. Let me just bring this down here. Give me 1 second. Okay, yeah. So we found out the equilibrium amount of the base. That means the anion salt of bases. Okay, it's anion salt of aces. It's not aces itself, but the anion salt. Okay, basically, if you talk about the anion salt, basically C4H9 N2O4S minus. This is the anion salt and this is the cation. Together they form a salt, but the base is the anion salt actually. Okay, so that's what we found out over here. Okay, this is the equilibrium amount of the base, basically of C4H9 N2O4S Na, because that's what we reacted initially, right? 3.5 grams of this, right? Remember that. Now there's another thing we need to write, the equilibrium amount of aces is 0.0100 moles. Okay, so what is aces actually? Aces is actually the weak acid. Okay, this is the weak acid. The anion of the sodium salt of aces is a strong base. So initially we had the sodium salt of aces, the anion. That means we had the base. Okay, so suppose if I say that ethanoic acid like CH3COH is an acid, its anion CH3COO minus will be a base. The anion will be a base. But look at this. Since ethanoic acid is a weak acid, its anion is a strong base. Similarly, aces is a weak acid, so its anion or sodium, the anion of the sodium salt will be a strong base. Similar logic applies here. Okay, so initially we had the strong base which we reacted with some HCl, and at the end of the reaction we had some excess base remaining, C4H9N2O4S remaining, and after reaction we got a salt, right? This salt, acid plus base, at the end of this reaction we got some aces, which is our weak acid. Okay, so at the end of our reaction we have 0.01 moles of aces, and the residual C4H9N2O4S remaining is 0.007148, which happens to be a strong base. The anion. Okay, this is basically the anion. Okay, now to find the pH of the solution you have two ways. You can either opt for the Henderson-Hasselbalch equation, which is pH is equal to pKa plus log base by acid. So pH is equal to pKa. You have the value of pKa given 6.88 plus log 0.007148 above base divided by acid. This is your acid essentially, divided by 0.0100. If you solve this using the calculator, you're gonna get your answer as 6.73. Okay. What's the other option? That recently in the mark scheme they aren't using Henderson-Hasselbalch equation anymore. Okay, they aren't using that anymore. I'll show you the alternate method that they use to find out pH, right? So we know that pKa is equal to minus log base 10 Ka, right? So 6.88 is equal to minus log base 10 Ka, or Ka is equal to minus 10 to the power 10 to the power minus 6.88, right? 10 to the power minus 6.88. So that's 1.32 into 10 to the power minus 7. That's all. Now, the alternate route is finding out H plus. This is the alternate route, the one in the mark scheme. Now, hear me out. So we know that we have an acid aces, right? So basically aces, right? Any acid, it breaks down to form H plus and A minus. Okay, it breaks down to form H plus and A minus, and anion and H plus. So basically aces also breaks down, right? Aces, the weak acid, it also breaks down to form some H plus as well as uh, the anion or the base, the one that we have. Now, Ka for this reaction will be the concentration of the anion or base multiplied by the concentration of H plus divided by the concentration of aces. We have all of this. Ka is 1.32 into 10 power minus 7. The concentration of the anion is basically, concentration doesn't matter. We're using the same volume, right? We're using a 250 cm cube. So all of it will cancel out essentially. That's why we won't show it. Okay, all of them have the same volume. We can directly use the moles. So base is 0.007148. 0.007148 multiplied by the concentration of H plus divided by this was 0.0100. Okay. Now if you want to find out H plus, it's going to be 1.32 into 10 power minus 7 into 0.0100 divided by 0.007148. Okay, this gives you a value of 1.86 into 10 to the power minus 7. Or an alternate option, if you use you know your calculator answers, you would get 1.8465 into 10 to the power minus 7. That's okay. Now to find out the pH of the buffer solution, pH is equal to minus log base 10 H plus, so that's going to be minus log 1.86 into 10 to the power minus 7. Okay, you're gonna get a final answer of 6.73. So that's the other option. I honestly prefer the Henderson-Hasselbalch equation. You'll get full marks for that as well. Okay, so that's it. It's a really hard buffer solution math. So yeah, if you have any other questions, please comment below. I hope you liked the video. If you did like it, please subscribe to the channel, and I'm gonna link the paper for Feb-March 2022 Vent 42 up here, and I'm going to link the paper for May-June 2021 Vent 42 down here. Okay, and the playlist for chemistry paper 4 up here, and remember to subscribe to the channel. And also, if you have other requests, please fill up the form I've added in the comments below. Okay, see you guys.